Welcome to Module 10. In this lesson, we will dive into inverter AC protection and coordination, one of the most essential skills for any solar or power engineer. Unlike inverters, which come pre-engineered by manufacturers, AC protection must be designed, sized, and coordinated by engineers. This module will give you the tools to do that confidently. AC protection matters because AC faults occur more frequently and propagate fast. Incorrect protection settings can cause nuisance trips, damage equipment, or even fail utility interconnection. Unlike DC protection, AC protection is fully the engineer's responsibility. Breakers, fuses, relays, and coordination must all be calculated. AC protection is built from several components. Breakers and fuses provide primary protection. Relays provide intelligence. CTs and VTs feed measurement signals. Trip curves define how devices behave and fault conditions. Understand each component is the foundation of proper coordination. AC faults come in several forms. Line to ground faults are most common. Three-phase faults are the most severe. High impedance faults and arc faults are harder to detect. In solar systems, invert fault current is limited, but grid fault current is very high. This difference is critical for coordination. Inverters do not behave like generators. Their fault current is very small, usually around 1.2 per unit, and lasts only a few seconds. This means breakers cannot rely on inverter fault current alone. Most AC protection must be coordinated based on grid fault current. Invert fault current is limited by control electronics, typically from 1.1 to 1.3 per unit for 2 to 4 seconds. The greatest contribution dominators, which directly affects breaker sizing. Before we talk about invert protection, let's first remind ourselves how traditional AC systems behave and faults. In a conventional generator-based system, fault current are very high, typically 6 to 10 per unit, and they last for several cycles. Because the photon energy is large, protection devices like breakers and fuses are designed with high energy trip curves. Coordination is also easier because the upstream and downstream devices see very different current levels. So their curves naturally separate. Traditional systems rely heavily on mechanical isolation, and the overall design philosophy is simple. Limit the photon energy and let the protection devices clear it. This is what most protection textbooks are written for, and it's very different from invert-based systems. Invert-based systems behave completely differently, and this is where many engineers get caught off guard. When a fault occurs, the inverter can only supply about 1.1 to 1.3 per unit current, and only for 2 to 4 cycles. That means the grid contributes most of the fault current, not the inverter. Because the fault energy is lower and short-lived, protection devices must be turning very carefully, especially the instantaneous region, to avoid miscoordination. Time grating becomes much tighter, and the curve overlap is a real concern. Utility also required electronics, anti-islanding, and transfer trip functions. Because mechanical isolating alone is not enough for invert systems. So the design philosophy shifts from limiting fault energy to ensure selectivity and fast clearing. This is the modern protection mindset for solar and base projects. In invert-based systems, protection must react fast and more precisely. Coordination depends on short duration, low energy photos, and tight timing grading. Here's a simple visual comparison to tie everything together. On the left, a traditional generator fits a brick and a load. When a fault occurs, the generator can deliver very high current, 6 to 10 per unit, and it lasts long enough for protection devices to respond using high energy trip cover. On the right, an inverter fits a brick and the grid. Its focus current is limited to about 1.1 to 1.3 per unit, and only for a few cycles. That means the grid supplies most of the fault energy, and our protection strategy must shift from fast clearing, tight coordination, and selectivities. This diagram highlights the fundamental difference in how protection logic must be designed for inverter-based systems. Breakers respond differently depending on current level. The thermal region handles overloads slowly. The magnetic region reacts faster to shoot circuits, and the instantaneous region trips immediately during severe faults. This curve shows how trip time decreases as current increases. The long time region represents thermal delay. The short time region allows brief inrush, and the instantaneous region trips immediately. Reading these curves correctly ensures proper coordination between upstream and downstream devices. Fuses have two characteristics: timings, melting and clearing, and their time current behavior determines how they respond to overload and faults. They are also current limited, which makes them ideal for transformer primary protection and coordination with breakers. This curve shows how a fuse behaves as current increases. Melting time is when the fuse element first breaks. Clearing time is when the arc is extinguished, and the I2T region represents the energy let through before the fuse fully opens. Coordination ensures that only the device closest to the fault trips. Upstream devices must wait longer. Downstream devices must trip fast. Selectivity prevents unnecessary outages. Time grading ensures proper sequencing. Overlapping curves indicate poor coordination. Coordination ensures only the nearest device trips. Upstream breakers act as backup, and the time grading prevents overlap between curves. This is the typical AC protection chain. Each device must be coordinated with the next. The invert breaker must trip before the AC panel breaker. The AC panel breaker must trip before the transformer primary fuse. The transformer secondary breaker must coordinate with utility requirements. Coordination is a step-by-step process. First, determine fault current, then plot all curves. Check for overlap. Adjust settings if needed. Validate selectivity. Finally, confirm with the utility. They always have final approval. We start by plugging breakers and fuse covers. Check for overlap. Then adjust settings until selectivity is achieved. This ensures smooth protection hierarchy. In this real project example, a 2 MW inverter operates at 600 watts and fits a transformer with a 25 kV primary. The primary fuse must be sized based on transformer in rush at the medium voltage side, while the signal breaker must be coordinated with utility fault current. This reflects real-world protection decisions. Many engineers make the same mistakes. Oversized breakers reduce protection. Slow fuses fail to protect transformers. Incorrect instantaneous settings cause nuisance trips. Wrong CT ratios distort relay behavior, and relying on invert fault current is a major misunderstanding. NEC provides several rules for AC protection. Article 240 covers breaker sizing and adjustment. Article 705 covers interconnection protection. Article 240.87 covers arc energy reduction. Those rules apply to US projects and must be followed. For Canadian projects, CEC rules apply. Section 14 covers protection devices. Section 84 covers base. These rules define break sizing, fuse selection, and coordination requirements. Canadian utilities also have strict protection standards. Utilities have their own protection requirements. They define fault current levels, break settings, instantaneous coordination, and transfer trip requirements. Anti-aliasing protection must always be included. Utility approval is mandatory. Manufacturers provide all necessary data. Break covers showing trip behavior. Fuse covers showing melting and clearing times. Invert datasheets showing fault current. Coordination tables helps engineers match devices. Always check interrupting rating. This slide shows a fully coordinated system. All curves are plotted. No overlaps exist. Selectivity is achieved. Settings are finalized. Utility approval is obtained. This is the final goal of AC protection engineering. Here all curves are plotted with no overlap. Selectivity achieved and utility approval confirmed. This is a hallmark of proper AC protection design. To summarize, always check for the current. Always plot curves. Always coordinate upstream and downstream devices. And always validate with the utility. Never rely on invert fault current. And document everything. Protection engineering must be traceable. In the next module, Module 11, we will start learning AC short circuit calculations. This is the foundation for all protection and coordination works. You will see how invert fault current behaves, how grid fault current is calculated, and how transformer impedance affects fault levels. We will focus on the basic concepts first, with clear diagrams to help you understand quickly. Module 11 builds the theory, and Module 12 will apply it to real project examples. If you found this module helpful, please consider liking the video and subscribing to Gamma Classroom. Your support helps us continue producing high-quality engineering content. Thank you for watching Module 10. See you on the next module.